Welcome back. 5.2.2, second day of 5.2. Other consequences of the mean value theorem. One of the main consequences of the mean value theorem is something called antiderivatives. So if you downloaded this file, you notice it was called antiderivatives. We're going to talk about what those are and what they mean in just a minute. First, quick recap of the mean value theorem and some of the implications of it. All right. When I teach this class live, I normally have students try to write from memory the equation associated with the mean value theorem and two things that have to be true about a function if the mean value theorem is going to apply to it. I would encourage you to do the same thing. Pause the video and see if you can remember these things from memory. It was just a couple of days ago that you learned it. Quite okay if you didn't have it memorized yet, but doing this type of practice will help you memorize it. Mean value theorem is one of the theorems you are going to want memorized for the AP exam. All right, the equation associated with the mean value theorem is f prime of c equals f of b minus f of a all over b minus a. Again, that f prime of c tells you the instantaneous rate of change. F of b minus f of a all over b minus a, that's average rate of change. And the mean value theorem says that as long as two things are true, the instantaneous rate of change has to equal the average rate of change somewhere in that interval. The two things that have to be true for that to apply are number one, the function is continuous, and number two, the function is differentiable. As long as you have a function that is both continuous and differentiable, then the mean value theorem applies. For any interval from b to a, that there is some value within that interval where the instantaneous rate of change is equal to the average rate of change. All right, the mean value theorem has several implications. Sometimes we call them corollaries, things that result from the mean value theorem. You don't have to know the word corollary, that's fine. But one of them is that functions whose derivative are equal to 0 are constant. In other words, if you know the derivative of f is equal to 0, then f of x is equal to some constant, right? Maybe f of x equals 8, or maybe equals 9, or maybe f of x equals 327. But if the derivative is equal to 0, then we know the original function was a constant, because that's the only time it happens, right? The only way for you to have a derivative equal to 0 everywhere is if the slope is equal to 0 everywhere, like that. And whenever that happens, the derivative is equal to some constant, right? In this case, y equals 4. All right, so if you know the derivative is equal to 0, like not just in a certain spot, but everywhere, then you know the original function was a constant, a flat horizontal line. Seems fairly obvious, but there it is. Corollary 3, functions with the same derivative differ by a constant. In other words, if I find f prime of x and g prime of x and they're the same, the only difference between them is a constant. So let's say f prime of x was 2x and so was g prime of x, right? If I worked backwards and figured out what f of x was, f of x would have to be x squared, because the derivative of 2x is x squared, and g of x would also have to be x squared. But they might have been slightly different. Maybe f of x was just f of x equals x squared. Maybe g of x was x squared plus 7, because that derivative of 7 would have been a constant, and they both end up with a derivative of 2x, right? So it's basically saying if you know that the derivatives are the exact same thing, the original functions are also the exact same thing, with the possible exception of differing by a constant. Maybe this one's plus 7, maybe that's plus 0 or plus 10 or plus whatever else you want. All right, here's where we come to something called antiderivatives. We're going to talk about them in a minute. This would be a good time to pause it and just think about this. If I told you f prime of x was equal to sine of x, what would f of x have had to have been? All right, well, the only way to get a derivative of sine, the original must have been not cosine, but negative cosine of x, because the derivative of cosine is negative sine, so the derivative of a negative cosine would be sine. However, this function is actually saying find all possible functions with a given derivative. And it could be negative cosine of x plus 2 or plus 7 or plus 896. Because remember, there could be some plus some constant, and the derivative of a constant is 0. So what we're going to put there is plus c. C just standing for constant, right? So the original function must have been negative cosine of x plus some constant, some c. That is what's called an antiderivative, right? The derivative goes one way, the antiderivative goes the other. It says if you know the derivative, the antiderivative would be your original function. So note antiderivatives. I'll come back to this one in a minute. Antiderivatives. 2 of x plus 5, an antiderivative of 2 of x plus 5 is x squared plus 5x plus 2. That's one example of an antiderivative because the derivative of this thing is 2x plus 5. Right? So antiderivative goes back to the original function. All possible antiderivatives of sine of x would be negative cosine of x plus c. The only difference between these two things, they're both antiderivatives. Right? The only difference is this is a particular antiderivative of that one. It's the antiderivative who has a constant of 2. And this is representative of all possible antiderivatives of sine of x because it's saying plus some constant. If I wanted a particular example of this one, a particular antiderivative might be negative cosine of x plus 9, right? If I wanted this one to represent all possible antiderivatives of 2x plus 5, I could say, well, it's going to be x squared, because the antiderivative of 2x is x squared, plus 5x, because the antiderivative of 5 is 5x, and then plus some c for some constant. And I just not going to say, like, I don't know what constant it is. All right, so that's some vocab around antiderivatives. Let's do this problem that I skipped. Find the function f with a given derivative whose graph passes through the point 1, 8. So here I'm given the derivative is 2x plus 5. Must be why I used that for my example. So I want to find the antiderivative, right? What would my original function have had to have been? Well, antiderivative of 2x, working backwards, would have been x squared, because the derivative of x squared is 2x. Antiderivative of plus 5 would be plus 5x, because the derivative of 5x is 5. And then it could be plus some constant, any old constant, I don't know what. This particular problem is asking me to find the particular function that would have passed through 1, 8. So it's giving me some more information to help me find that constant. I know with my function, when I plug a 1 in, I should get an 8 out. So I say, oh, well, I do know when I put a 1 in for x, 1 squared plus 5 times 1 plus whatever that c is, I should get an 8 out. Solve for this, we could find our c. 8 would equal 1 plus 5 plus c, so c must equal 2. So now I can rewrite my original function must have been x squared plus 5x plus 2 for this particular one, right? So my particular antiderivative for this function here is x squared plus 5x plus 2. The antiderivative in general, all possible antiderivatives are represented by that equation. But this particular antiderivative is the only one, right? That particular one there is the only one that goes through the point 1, 8. Last type of problem, finding velocity and position. Find the velocity and position functions of a body falling freely from a height of 10 meters under each of the following conditions. So I've got this problem. We're going to do the problem twice apparently. A, the acceleration is 9.8 meters per second squared, and the body falls from rest. Falling from rest means it's falling from, you just hold it, it's not moving, and then it falls. So let's start with this. Acceleration. Well, acceleration due to gravity falls downward. So I like using that acceleration as a negative 9.8 meters per second. Some people use it as 9.8 meters per second, and they just know that their velocity is a downward direction. I always like using it as a negative though. So For A, I'm going to have AB acceleration. Acceleration with respect to time is negative 9.8. Not negative 9.8 t, just negative 9.8. Acceleration due to gravity is a constant. All right, if that's acceleration, I can find velocity. Velocity would just be the antiderivative, right? Working backwards. It's going to be 9.8 t, since my variable is t, plus some constant, right? To figure out what that constant is, I need a little bit more information. Luckily, they gave me some information. They said the body was falling from rest. That means when I plug in a 0 for the t, I should get a 0 out for its velocity, right? It's starting at a velocity of 0. So I could say, all right, well, with that acceleration, that velocity function, I know when I do v of 0, when I plug in a 0, negative 9.8 times 0 plus c, I know I should get out a 0, right? At time 0, I should have a velocity of 0 because it's starting from rest. In this case, it looks like 0 must be equal to c, which makes my velocity equation pretty simple. Just negative 9.8 t. So now I've got myself an acceleration function. I've got myself a velocity function. The last thing I was asked to find was the position function. Well, position would be the antiderivative of velocity, right? So do this one more time. My position function would be the antiderivative to that. Well, so since I've got a t here, the antiderivative working backwards must have had a t squared there, right? So that when I take the derivative, I end up with a t. So in front of that must have been a negative 4.9. Where did the 4.9 come from? Well, when I take the 2 and bring it down there, 2 times a negative 4.9 is 9.8, right? So that's where it's so like, oh, that must have been a 4.9 because 2's got to come down and multiply by that. Oh, plus some c, right? Because again, it's going to be some c. So then to figure out this c, I need a little bit more information. Preferably some information that has to do with position. So let's look at this thing. Let's see here. The original problem said find the velocity and position functions of a body falling freely from a height of 10 meters. There you go, under each of the following conditions. It fell from a height of 10 meters. In other words, when time was equal to 0, the height was equal to 10. So plug that in. When time was equal to 0, height was equal to 10. Multiply by 0, it looks like 10 would equal c in this case. So my position function is negative 4.9 t squared plus 10. All right, let's do this one more time, but this time, instead of falling from rest, our body is being propelled downward with an initial velocity of 2.5 meters per second. All right, so part A. Looks like acceleration's the same, right? Earth hasn't changed size. So the acceleration is still negative 9.8. Again, negative because gravity pulls downward. Velocity then would be negative 9.8 t plus some constant. To find that constant, I need to plug in a little bit more information. They told me the initial velocity was 2.5 meters per second. The initial velocity would be the velocity at time equals 0. So I know when I plug in a 0 for my t, I should get out a 2.5 for my velocity. In that case, 2.5 is equal to c, right? Because 9.8 times 0 is 0. We should have that. And I've got my velocity function. It's not just negative 9.8 t plus some random c. The c in this case is 2.5. All right, got my acceleration function, got my velocity function. Last thing I need is a position function. So we do the antiderivative one last time. Antiderivative of negative 9.8 t is again negative 4.9 t squared plus antiderivative of 2.5 is 2.5 t plus some constant. To figure out that constant, plug in the last information. Again, we're started from a height of 10 meters, so I know at time t equals 0, negative 4.9 times 0 squared plus 2.5 times 0 plus c. When I plug in a 0, I should get out a 10, which would make c again 10 in this case. And I've got my final position function. Negative 4.9 t squared plus 2.5 t plus 10. All right, your assignment, 29 through 35, those are finding antiderivatives, 38, 43, and 44. 44 has an asterisk. It says, note, it requires knowledge that the acceleration due to gravity is 9.8 meters per second squared. We did that with the last two examples, but your book doesn't just tell you right out. So be aware, acceleration due to gravity, 9.8 meters per second squared. Negative if you want to consider gravity, that gravity pulls downward.